Hi everyone, and welcome to the Organic Chemistry 1 review activity video key. So I'm going to take you through all of the questions and give you some hints as to how I think about things, and perhaps that will help out. Okay, so the first question is to draw all 9 constitutional isomers of C3H6O, and it gives some hints as to what functional groups will be present. If we do a calculation of the hydrogen deficiency index for this molecular formula, we would do 1/2 2 times the number of carbon, which is, since there are 3 carbons, 2 times 3 is 6, plus 2 minus the number of hydrogen, and oxygens don't go into the formula. We would have additional information here if we had any halogens or nitrogen, but oxygens, the number of oxygens don't change the hydrogen deficiency index. So this is 1/2 of 2, which is 1, and that tells us that there will be 1 pi bond or 1 ring in each compound that matches this formula. So if we look at some of the hints, right, there is 1 aldehyde. So we have 3 carbons and an aldehyde. So the only way to get an aldehyde is to put the carbonyl at the end, the terminal carbon. So for example, if I was to put the carbonyl here, then sometimes people draw in that hydrogen. That is an aldehyde that matches the formula. We have 1 ketone, so we could also have 3 carbons in a row and instead put the carbonyl in the center, and that would be a ketone. And 1 ether, right? So how do we get 3 carbons in a row with an ether? So the ether means that you're going to have 2 carbons, right, on either side. So perhaps, right, we need another carbon. And then think about the fact that this isn't going to match the formula, because right now this does not have a pi bond or a ring, right? So maybe we need to throw in a pi bond so that we can get an ether, okay? 3 compounds with an alkene and an alcohol. Okay, so 3 different compounds where we have an alkene and an alcohol. So for example, maybe we had our 3 carbons like this with an alkene, so I drew in an alkene there. Now we just need to add an alcohol. So perhaps we could add in the alcohol at this terminal carbon over here on the right. If we use that same carbon scaffold, maybe we can put an alcohol at the center carbon, and then perhaps even at the carbon on the left. And 3 cyclic compounds, right? So we need to make a ring, and it says 2 of which are ethers and 1 is an alcohol. So maybe if we have a ring, right, with 3 carbons and an oxygen, we could get a 4-membered ring like that. This would match the formula. Remember, we don't need to have any pi bonds here because the ring takes care of the unit of unsaturation. It's also possible to have a 3-membered ring, so maybe a 3-membered ring ether with a carbon outside of the ring, like a methyl group. Or maybe also possible to have 3 carbons in the ring and the alcohol outside. So that's a 2 are ethers and 1 is an alcohol, so that matches the hints. There is no particularly easy way to come up with all the structures. That's why the hints are there. You just kind of have to play around with moving groups around to different positions to try to think of more constitutional isomers. But just as a review, the definition of a constitutional isomer are compounds with a different molecular formula. Oh, sorry, the same molecular formula, but different atom connectivity. So that means the atoms are connected in a different way, right? But they all share the same molecular formula. Okay, Moving on to question number 2. Circle and name the functional groups present. Okay, so you can really start anywhere here. This carbonyl with 2 carbons on either side, this is going to be a ketone. Right, this carbonyl has an oxygen on one side that has an R group attached. Right, so this is an ester. This carbonyl has an oxygen on one side and a hydrogen attached to that. So that makes this a carboxylic acid. Right, so note that this is not an alcohol, right? Because of the carbonyl next to it, it's considered a carboxylic acid and not an alcohol. This OH group, though, has a carbon that doesn't have a carbonyl next to it. So this one is an alcohol. And then the last one we have here is this SH group attached to a carbon, so this is called a thiol. All right, moving here to the compound on the right. Looks like we have a carbonyl with a hydrogen directly attached, right? So this is an aldehyde, right? Carbon-carbon triple bonds are called alkynes. And then an oxygen with 2 R groups on either side is called an ether. Right? This alkene, even though it's part of a ring, it's still an alkene. Sorry, that should be an E. Hopefully everyone can see that. And then when you have a halogen attached to a carbon, as long as there's no carbonyl here, it's called an alkyl halide or chloride in this particular case. And now we have a carbonyl directly attached on one side to a nitrogen, right? So that makes this an amide. In contrast to a nitrogen that's attached to a carbon that doesn't have a carbonyl, right? This one is called an amine. Okay, that's a good review of your functional groups. Moving on to question number 3. Draw all significant resonance structures of the following compounds and label the most significant contributors. Draw in any missing lone pairs as needed and use proper arrows. Okay, so I always like to start with the lone pairs if they're not drawn in, and the one that I see is the lone pair that's on the nitrogen to make an octet for that nitrogen. So we're going to start drawing some resonance contributors. When you see a charge, it's a good idea that you're going to involve that charge in the first contributor. So this pattern looks like the allylic carbocation, right? Or allylic positive charge is sometimes called. So to draw that pattern, we're going to shift the pi electrons over to between these 2 carbons. When I'm drawing resonance contributors, don't forget to draw that resonance arrow. That's super important to show that we are drawing, we're not drawing actual changes, just different resonance contributors. So draw the structure that you just formed with your arrow, which is moving the positive charge over here and the pi bond shifted over. Next, we have a lone pair adjacent to a positive charge, right? So that is an important pattern as well. I actually think I'm going to draw these arrows in a different color just to sort of highlight them. So I'm just going to draw. So this pattern is pi bond adjacent to a positive charge. And resonance can be reviewed at the end of chapter 2 in your Klein textbook. Right, so when you have a lone pair adjacent to a positive charge, it can be shared through the formation of a pi bond. So we formed the second pi bond here, and that Now the positive charge is on nitrogen. Notice that each structure has one positive charge. So when you start out with a charge, that charge will be present on every single structure, and there won't be any other charges because the sum of the charges have to be the same in each contributor. So that means that if, in order to get more charges and still have a sum of +1, you would need a plus, a negative, and a plus to sum to +1. Three charges in a structure is too unstable, so it's considered an insignificant contributor. Right, so these are the three different resonance contributors. And if we look and see, okay, which one is the most significant contributor, it is actually the one on the right here. And the reason for that is because these two contain a carbon with a positive charge. So that carbon lacks an octet. And by definition, it's going to be less stable if there's an atom that lacks an octet. Whereas in this structure, all of the atoms have an octet. So this is definitely the most stable. All right, moving on to the next one here. We're going to draw in our lone pairs, if they're not already drawn in. And then as I mentioned, usually if you see a charge, you want to start there with your pattern. What I'm noticing here is the allylic lone pair pattern. Right, so we have a pi bond and one bond away is a lone pair. So this is an allylic lone pair. We need 2 arrows to show the delocalization of that lone pair. And we can move it to every other atom. So it moves from this carbon, skip 1, to that carbon. Okay, that gives us this resonance contributor, and you might notice that it's still allylic to this pi bond. We can keep going with the same pattern and move the lone pair all the way up to the oxygen. Okay, and there's nothing else we can do here. Notice how each structure has one negative charge. So if you forgot a charge and there's no charge here, right, you just know immediately, okay, I'm supposed to have a negative charge on every single one, so maybe I forgot if I don't see one on one of my structures. Okay, the most stable, right? So the lone pair, if you have to have it, is more stable on a more electronegative element. So it's more stable on oxygen versus carbon, right? So this one is the most stable. Okay, continuing with resonance on the next page. So we have an ether here. I'm going to go ahead and draw in some lone pairs. And I want to look for any patterns. There aren't any charges here, right? So that doesn't give me any clues as to where I should start. But one thing I might notice is that this, one of these lone pairs, is allylic to this pi bond, right? So that means it exists in a p orbital that overlaps with the neighboring p orbitals, right? So we can show delocalization here. This is an sp3 hybridized carbon. So this pi bond is completely isolated from this other pi system because there are no p orbitals here to overlap with the p orbitals there. So we can't do anything with this pi bond in terms of resonance. So the one thing that we can do is the allylic lone pair pattern, starting on the lone pair and moving electrons to the left. When you start with a neutral structure, if you're able to draw a resonance structure, that structure will have a positive and a negative charge that sum up to a net zero charge, right? So that matches the net zero charge in the first structure. In terms of the most stable, it's going to be by far more stable to have no formal charge than to have 2 formal charges. right? So this one is the most stable. Moving on to the next one, we have carbonyl. We're going to draw in some lone pairs. So again, we're starting with something neutral, right? So we need to look for a pattern. The pattern that I see is the pi bond between atoms of differing electronegativity, right? And that happens with any carbonyl. So we can move electrons up to the more electronegative oxygen atom. Remember that you're going to generate a positive and a negative charge. So if you forget one, right, you just always double check that the net charge in each structure is the same. Okay, once we have this, we might be able to recognize that this is a allylic positive charge. So we can shift these pi electrons over. Don't forget your positive charge has shifted over as well. In terms of the most stable, again, this one has no formal charge, so it is definitely the most stable. In addition, these lack an octet, these two carbons with the positive charge, so those are less significant because of the octet rule. Okay, the last one is an ester. We have some missing lone pairs we can go ahead and add in. Again, we can start with the same pattern that we did up here, the pi bond between atoms of differing electronegativity. Move electrons up to the oxygen. That will give us our positive and negative charge. And then we now can visualize a lone pair adjacent to a positive charge. So we can share that lone pair as a pi bond. Okay, those are our three resonance contributors of an ester. And again, the one with no formal charge is definitely the most stable. Moving on to question number 4. Consider the ester functional group shown in the structure below. The reported pKa of methyl acetate is 25. This value is much less than the expected pKa value of 50 for a normal carbon-hydrogen bond, particularly where the carbon is sp3 hybridized. Which of the CH bonds is responsible for the low pKa value? Explain why methyl acetate has such a low pKa value compared to a normal alkane. Okay, so if you've done an analysis here, you might have recognized that actually the hydrogens here on the left are the most acidic. And let's look at why. If we remove one, right, we can draw the conjugate base. So we can go ahead and remove one of those to draw the conjugate base. If you remove one, there'll still be two there. You can draw those in if you would like, or leave them out. Right, so there's still two hydrogens here and now one lone pair and a negative charge. I can go ahead and add in some additional lone pairs on this structure. So what's different about this structure compared to a negative charge here or a negative charge here? The difference is that while the negative charge would be on a carbon atom in all cases, this particular negative charge is delocalized or resonance stabilized. So we can move the electrons up to the oxygen. To show that electron delocalization. Right, so this one we would call it an allylic lone pair. It's delocalized, it's resonance stabilized. Right here are the resonance contributors. Whereas if you had a lone pair, or if you had lost a proton on one of the other carbons, for example, on this carbon, right, this is not considered, there's no resonance stabilization here. There are no resonance contributors we can draw, right? In addition, same thing if you had removed a proton on the end, right? This is not resonance stabilized at all, right? So these have no resonance stabilization, right? So they're not very stable, which means that those protons are not very acidic. Whereas here, if you remove one of these, we do have resonance stabilization, which makes that lone pair much more stable, and therefore the hydrogen here much more acidic. So it's actually one of these three hydrogens at the end that has a pKa value of 25. The hydrogens over here would be much less acidic with a much higher pKa value. Moving on to question number 5. Draw the Newman projection of the following compound, oh, it says compounds, excuse me, compound about the indicated bonds, right? So we are just going to put our eyeball up here, here's our eyeball, and look down this carbon-carbon bond. So when we're drawing our Newman projection, we do circle and a dot, right? The dot is the front carbon, which is this carbon number 1. And the circle represents the back carbon, or carbon number 2. So carbon number 1 has an OH group pointed straight up. Right, if you can visualize that from your viewpoint. And then coming out of the plane of the paper is a methyl group. So that would come off to your left from your viewpoint. So we're going to put methyl over here. And then the hydrogen is going back, which would go to your right from your viewpoint. And then in the back, we have a methyl group pointed straight down. Right? And then we have chlorine coming out to your left and the fluorine going into your right. Right? So this is the Newman projection of that particular compound. Newman projections can be reviewed in chapter 4. Okay, the next question says, draw a chair conformation of the following molecule, ring flip your original chair, and circle the more stable conformation. And I added in the activity, if applicable. And we'll see why I added that. Okay, so we can start with the cis 1,2-dimethyl cyclohexane. Perhaps you'd like to visualize that out in a line structure first. So cis just means both up or both down, and it doesn't matter which one you pick. So for example, we could put both of our methyl groups up, and they would be cis. So in drawing the chair conformation, right, I like to draw my 2 parallel lines first, with the one that's higher going further up. Draw in a 90-degree angle from those 2 parallel lines and then connect them. Okay, so I can put the methyls anywhere, but it's common to kind of visualize them at the ends here. So if one methyl is up, I'm going to put it in the up position, which is up and axial. And the next methyl is also up, and in this case it becomes up and equatorial. Right, so these are my methyl groups. I could label them if I want to, so it's more clear. Right, and then if I do a ring flip, when I draw the other chair, I sort of go down and to the left. Remember the line that's higher up goes further up on the paper. 90-degree angle from there, and then connect. Okay. And then just note that this carbon, right, is now this carbon. So it is sort of dipped down in the ring flip. Okay, so I'll just kind of circle that just so that it's clear, right, where that carbon is after the ring flip has occurred. The methyls still need to be up, but it goes from up and axial to up and equatorial during the ring flip. And then this would be the carbon going clockwise, right? So it would be the next one over. And remember that the methyl is going to go from up and equatorial to up and axial, which would be here in this carbon. So in each chair conformer, we have one methyl that is axial, one methyl that is equatorial. So these are actually equally stable, right? So there's no difference energetically between the two because each one has the same group, either axial or equatorial. Okay, moving on to determining the R and S configuration of all the stereocenters in the following molecules. Okay, so we're going to look for carbons where there's 4 different groups attached, right? Like, so for here, there's the fluorine pointed coming out and the hydrogen going back, and here there's an oxygen coming out and a hydrogen, or sorry, pointed back and the hydrogen coming out at you. So we can draw an arrow from 1 to 2 to 3, right? So fluorine would be first between these 2 carbons. This has a higher priority, and then this one has the 3rd priority, right? So 1 to 2 to 3. Okay, so 1, 2, 3. And the hydrogen pointing back, so counterclockwise, is S. Okay, over here we have the OH group. CH2 and CH2 is a tie, but this carbon has a fluorine attached and this one doesn't. So this is going to get priority 2. So 1 to 2, coming around to 3. Okay, this is also counterclockwise, and it looks like S, except for the fact that we're actually looking at it from the wrong direction because the hydrogen is coming out at us instead of pointed back. So this is actually R. Okay, in a Fisher projection, we just need to remember that this, even though everything is drawn flat, this actually means, so if I kind of draw this again, the groups on the horizontal are actually coming out at you, right? And the groups on the vertical are pointed back, right? So these are also coming out at you. So we'll draw wedges here. So we have the OH, OH, hydrogen, fluorine, hydrogen. So this is important to keep in mind when we're determining R and S here. Okay, so for the top one, right, we have priority group 1 is the OH, right? Between these 2 carbons, this has a higher priority than this one. And this is priority group number 4, so we don't worry about it. So we go from 1 to 2 to 3. I did overlap 4, but that doesn't matter. Right, so this is 1, 2, 3. That's why I drew the arrow in a clockwise manner. But with the hydrogen coming out at us, and we know that it is because it's on the horizontal, then we flip it, right? So this is actually S. On the bottom here, the fluorine actually has the highest priority, then the oxygen, then the carbon. So fluorine, oxygen, carbon. I'm going to draw my arrow like that. Now the hydrogen is pointed back, which is the 4th priority group, and we want it pointed back. And so when it is, then this counterclockwise rotation remains S. Okay, for the next one, this is drawn in a Newman projection. It can be difficult to determine the stereochemistry in a Newman projection. So one thing that we can do is take it out of the Newman projection and go back to a regular dash wedge conformation. So what you can do is imagine sort of looking, right, draw the carbon bond for the two carbons, so the front carbon and the back carbon. And then I'm just gonna put my eyeball over here. It's just my personal choice. You could do it differently, which means this is the front carbon and that's the back carbon. So on the front carbon, I can put my hydrogen, which is this one, pointed straight down, right? Then I know that I have a wedge and a dash, okay? And from my viewpoint, I think to myself, okay, whatever is on the wedge is going to be to my left. So that's actually the fluorine. I'm going to put in fluorine and chlorine. And then over here, pointed directly straight up, is an OH group. Right? And I know I'm going to have a group on a dash and a wedge. I'll draw those in. And then again, from my viewpoint, right, or on the same side as the fluorine is a hydrogen. So on the same side pointed out as the fluorine, I'm going to draw the hydrogen. On the same side as the chlorine is the methyl. Okay, so that's one way you could view this out of a Newman projection and back into a dash wedge conformation or line structure. Okay, so for the top one here, right, we're going to determine the priority group. So it's looking like OH first, this carbon next, that carbon last, right? So sort of 1 to 2 to 3. It looks like clockwise, but the hydrogen is coming out at us. So we actually know it's going to be counterclockwise and S. This one is a little bit more challenging because the fourth priority group is in the plane, right? So you have some options here. You could do a rotation to get it going back, right? Or you could redraw this where you switch two groups, right? So for example, I could redraw and I could keep the back one the same, the back carbon. I'm going to put my methyl. So I'm just redrawing the back carbon exactly the same, right? And then what I can do is start flipping groups around, and I can keep it really looking with all the dashes and the wedges exactly where they were right before. I'm just going to now switch some groups, and or you can do a rotation. In this particular case, since I didn't really switch this group, right, I might switch two groups and that's it, and then note that if this is R, then this is S, or you can kind of just rotate. It's totally up to you how you want to do it. Let's try the flipping two groups. So if I do a chlorine, right, if I want to move the hydrogen, I would like to move it to the back because this is my lowest priority group and I would like it to be in the back. So then I might put the hydrogen there and the chlorine here. If I leave the fluorine where it is, then I've basically just switched only two groups, so the chlorine and the hydrogen. So when I come up here and determine the whatever this is, if it's R, then this will be S. If this is S, then this will be R. Right? So you have to just remember to switch it back. So in terms of the priorities, right, we have, it's based on atomic number. So chlorine is first, fluorine is second, and carbon is third, right? So 1 to 2 to 3, and this is counterclockwise, and the hydrogen pointing back, right? So this one is S, which means this one is R. Okay, so there's a lot of strategies on how to do it. That's just one way. There are other ways, like you could just literally just rotate these groups, and that would also work. Okay. So the next one, we have trans 1,2-dimethyl cyclohexane. Right. So in terms of the priorities, right, for this carbon. We've got, this one is the highest priority because it's going to have 2 carbons attached, then this one that has 1 carbon attached, then this one that has only hydrogens attached. So it's going to go 1 to 2 to 3, okay, with the hydrogen pointing back in this case. So this clockwise is truly R. And then over here, it rotates in the opposite direction. So 1 to 2 to 3. But remember that the hydrogen is coming out at you in this case. So it is actually a clockwise and another R rotation. Okay, the next one, we just need to determine our groups. So oxygen comes first, carbon and carbon and carbon is a tie, right? Whereas this one has the sulfur attached, it'll be the next highest priority. So 1 to 2. Coming up here to 3, right? The methyl that's pointed back is your 4th priority group, and it's convenient that it's already pointed back. That's good. So that just means clockwise rotation is R. And down at the bottom here, we have the sulfur is the highest priority, right? Then this carbon at the top, then this carbon. And now our 4th priority group is coming out at us, right? So this clockwise rotation is actually counterclockwise, and this is S. Okay, the last one here, we've got the chiral carbon at the top, right? This is not a chiral center because those 2 groups are identical. So it might look like it because there's a dash and a wedge, but it's not actually one. In terms of priorities, we've got the oxygen, carbon, and then this carbon. So 1 to 2 to 3, I do my little arrow here. The 4th priority group is coming out at you, right? So it's actually counterclockwise in S. Down here we have got the fluorine, right? Then we have this carbon, then we have the other. The hydrogen is pointed back as it should be, so counterclockwise is S. Okay, let me know if you guys have any questions about any of this. You can post in the discussion board or come to an office hour or email me. All right, predict whether each of the following carbocations will rearrange. If so, draw the expected rearrangement using curved arrows. So whenever I have a secondary carbocation, I'm always very suspicious that there might be a rearrangement because secondary carbocations like this one are not very stable. So if I do a hydride shift over here, that's just going to get me another secondary carbocation. So it's actually best to shift the methyl over. And so that is going to give us, after the shift, right, we've shifted a methyl over, we've got the methyl that remains, and now the positive charge is here. So it went from secondary to tertiary, which is more stable. This carbocation is already tertiary and allylic, right? So it's already very stable. There's no shift that's going to make this more stable, right? So this one will not undergo a rearrangement, right? Rearrangement, because it's already tertiary and allylic. This is a secondary carbocation, and like I said, I'm always suspicious of those. Maybe we can do a rearrangement, right? And it's symmetrical, so you don't really need to worry about which carbon you do a shift from. But if you do a hydride shift, the question is, does that make it more stable? And the answer is yes, right? It does make it more stable because even though it's still secondary, now it's secondary and allylic, which makes it more stable. Right, so this went from a secondary to a tertiary. This one is already tertiary and allylic, so it's very stable. This one went from secondary to secondary allylic. Right, and resonance stabilization always makes something more stable. Okay, the next one is about drawing in arrows. So drawing in the missing curved arrows for the following mechanism and identifying the arrow pushing pattern associated with each step. And we're either going to call it a proton transfer, a nucleophilic attack, a loss of a leaving group, or a rearrangement. So we just have to carefully analyze what's happening here, right? What's happening is there's a proton transfer from hydronium ion to the oxygen, one of the lone pairs on the ketone. So we can show that proton transfer. We can show it picking up a proton. And we can label that step as proton transfer. Okay, from what's happening if we analyze this next step is it looks like the nitrogen's lone pair is doing a nucleophilic attack, right? So it's doing a nucleophilic attack and we have a resonance arrow. Okay, so those are the arrows needed to move the electrons to make this product, right? So this is a nucleophilic attack. All right, what's happening from here to here? It looks like we are losing a proton, one of the protons on this nitrogen. So they've already drawn in water for us. That's great. We can use water as a base to remove that proton. So this is another proton transfer. You can see the proton was transferred to water, so we formed hydronium ion. So what's the difference between here and here? It looks like we are actually gaining a proton on this oxygen, whereas we only had one here, now we have two. So we're going to be doing another proton transfer. Okay, so I'm going to draw that in, proton transfer. What's happening in this next step, it looks like we're losing this water, which could be a leaving group, right? And we're forming this pi bond that we see here. So we have loss of a leaving group, water is leaving, we even see minus water here over the arrow, and then the formation of that pi bond. Right, so this would be loss of a leaving group. From here to here, it looks like we're losing this proton on the nitrogen. So we can go ahead and use water to take that proton and then go ahead and label it as proton transfer. Okay, from here to here, it looks like we're gaining that proton back on the oxygen here. So we can just go ahead and do another proton transfer. Notice that a lot of the steps are proton transfer steps, and that's very common in mechanisms, particularly ones that occur under acidic conditions, as this one does. Okay, next, looks like we're forming a new bond between this nitrogen and the carbon, because we can see that new bond is formed here. So we're going to do a nucleophilic attack on that carbon to form that bond, and a resonance arrow to move electrons up to the oxygen to avoid exceeding the octet on that carbon. Right, so this is a nucleophilic attack. From here to here, if we analyze what's different, it looks like we're losing a proton on the nitrogen. So they've drawn in water again. You can go ahead and use water to come and take that proton. Okay, and then looks like we're gaining that proton on the oxygen. So we can go ahead and pick up a proton on the oxygen, so another proton transfer. And we're going to lose water again. We notice that water is not there, right? So it's getting kicked out, loss of a leaving group, and we're going to use the lone pair on nitrogen to form a pi bond, right, which is a resonance arrow. And then it looks like at the end, water will come and take this final proton in order to isolate a neutral product. Okay, so hopefully that makes sense to you. Let me know if it doesn't. Predict which of the following, A or B, occurs faster under solvolysis conditions. Right, so solvolysis means that the solvent is getting involved in the reaction as a nucleophile, which means that methanol is going to be our nucleophile, which is also our solvent in this case. So we're really wanting to know which one occurs faster, which of these SN1 reactions occurs faster. So solvolysis can also be AKA, typically an SN1 reaction. Right, so in an SN1 reaction, the loss of the leading group is the rate determining step. So this first step where we lose the bromine, right, this is the rate determining step of an SN1 reaction. And they didn't draw it, but we also get some bromide here in that step. Okay. And then a series of steps occurs where methanol does a nucleophilic attack, followed by a proton transfer to get these products, right? So there's going to be 2 more steps in the SN1 mechanism, right, where we have the nucleophilic attack, right, of methanol and proton transfer. Okay, so same thing in this case. But really those steps don't matter. Okay, so nucleophilic attack followed by proton transfer. Because they're not the rate determining step, it doesn't matter, right? What we actually care about is this first step, and that's because it's the rate determining step. So in the reaction, we've got the same leaving group. So those have the same stability. But it's a question of which one of these 2 is more stable, right? And there's a couple of lone pairs on that oxygen. I can go ahead and draw that in. It's actually the top one that is more stable. And it's because of the additional resonance stabilization that is afforded by the oxygen's presence. So if we draw out that intermediate, the positive charge here, right, we can show some resonance. So this is the allylic carbocation or allylic positive charge pattern, right? Notice the resonance arrow, so I am drawing resonance contributors. Right, now the positive charge has moved over. Now we have lone pair adjacent to a positive charge to get the last resonance contributor. So what's special about that is that it doesn't exist with the pathway labeled B, right? Because there's no oxygen here, it doesn't have this third resonance contributor. So this one with 3 resonance contributors, right, is a more stable intermediate, right? It has greater electron delocalization. So pathway A, right, is faster because the energy of the intermediate is lower, it's more stable. So that means that the activation energy to get to this more stable intermediate will be lower. Okay, so, and it also asks us, right, in which pathway, SN1 or SN2? And the answer is SN1. Does the solvent usually participate in a chemical reaction? Okay, so then down here it asks us true or false. Although oxygen is an electronegative atom, the lone pairs on oxygen can be used to donate into electron deficient systems like carbocations, thus making the oxygen atom or group an electron donating group, and that is true. Right, so you might think that the oxygen's presence here is destabilizing the positive charge by withdrawing electrons, right, through induction, and that's true. So this sigma bond, right, is polar, and the more electron density is around oxygen than on carbon. So that actually makes this carbon have more of a positive charge and destabilizes it. However, the lone pair is able to be donated through resonance. So inductively, the oxygen withdraws electrons, but through resonance or the pi system, right, it donates electrons. And resonance is just usually a more dominant factor compared to induction. So yes, it withdraws electrons through the sigma bond, but it donates electrons through the pi bond. So it actually overall helps to make this more stable, right, by delocalizing some of the pi electrons, even though it is withdrawing through the sigma bond. Okay, the next question, number 11. Provide a reasonable mechanism that accounts for the stereochemistry of the following reaction. And then I think I added something in your activity that talks about how the product is a racemic mixture. So this is a chiral center, right? Which they didn't draw anything with a dash or a wedge, which is one way to indicate that you get both. Okay, you get both enantiomers there. So in terms of the mechanism, right, we have a weak nucleophile / weak base in methanol, and it is getting incorporated as a nucleophile. So we're definitely doing an SN1 reaction because of the weak nucleophile, right? A tertiary carbocation is going to be very stable. So the fact that this is a tertiary alkyl halide is great because the rate determining step is this first one, which is loss of a leaving group, right? And if it forms a stable tertiary and resonance stabilized carbocation, that's going to happen very quickly. Right, so that's rate determining step. And then we just need to draw resonance in order to show that this positive charge is not really localized on this carbon. Instead of that, it's actually delocalized on this carbon, and this carbon. Right, so we can draw a series of resonance contributors now, where the pattern is the allylic positive charge. So I've shifted electrons, and then I can just keep going. So there's a total of 3 resonance contributors here. Sometimes when resonance is part of a larger mechanism, we put brackets around it just to show. These aren't really true steps. These are just showing different resonance contributors, which all together make the same structure. So what does this mean? It means that the positive charge is not really localized here. It's delocalized between here, here, and here. Right? So this carbon has some positive charge. So it's not too unreasonable to think that our methanol will sometimes attack a carbon other than this one. And for example, perhaps this one. Now, as soon as this leaving group has left, right, what used to be a chiral center is now trigonal planar and has no chirality. Right? This is no longer a chiral center. And this is also not a chiral center. So this is trigonal planar with an empty p orbital on that carbon. Methanol can attack from the top or from the bottom of that planar structure with equal probability, leading to a mixture of enantiomers. So that's where you get the chirality. So we can say this step leads to a mixture of enantiomers. So we can go ahead and draw that out. This is the initial product of that nucleophilic step, nucleophilic attack step, which would then need to lose a proton to become the final product. So note that, right, this is a stereoisomer center, and it is a racemic mixture of the two enantiomers. Okay, so another methanol can act as a base in this SN1 reaction and can come in, take that proton, and we'll end up with the product and the conjugate acid of that step. Okay, so again, the reason why we end up with a mixture here is this is planar. So the nucleophile can attack from either the top face, which would mean that this would be on a wedge, or the bottom face, which would mean that this would be on a dash, right? And we would end up with the two enantiomers of that. Okay, next is predict the major product of the following reactions and show a mechanism to explain its formation. Okay, so when it says acid, right, that H2SO4 cannot exist in a reaction by itself. It's going to be aqueous. Even if it doesn't say aqueous, it's going to be aqueous, which means that an aqueous solution of sulfuric acid is really just hydronium ion in solution and water. Right? So what we have in solution is really hydronium ion and water. Heat is a dead giveaway that this is going to be doing an E1. Right? And so then the reagent is not really the acid, it's actually water. Water is a weak nucleophile / weak base, so it can do SN1 or E1. With heat, E1 is favored. So we're going to be doing E1 here. So what's going to happen with an E1 is that the leaving group needs to leave to form a carbocation, but before that can happen, we need a good leaving group. So we need to pick up a proton to form a good leaving group. Now this is a good leaving group because once it leaves, it becomes water. Right, so we can do loss of a leaving group. That gives us a nice and stable tertiary carbocation and water. And now we can do the E1 reaction. E1s always form the Zaitsev product as the major product. So we're going to actually draw in one of the hydrogens on one of these two beta carbons, right? Not worrying about the hydrogens on that beta carbon, because removal of one of these two leads to the more stable, more substituted product, which we call the Zaitsev product. Okay, so that will give us the Zaitsev product as the major product. So this is major, and sometimes it's called Zaitsev product. And we also form some H3O plus as a byproduct in this last step. The next one has this alcohol, and again it's H2SO4 and heat. So it's very similar to the last one that we just did, right? We're going to have hydronium ion. It's going to go do an E1 pathway. I'm going to draw in some hydronium ion. Right, the point of that is to have a strong enough acid in solution to make a good leading group here. Now that we have a good leaving group, we can leave. In this case, forming a secondary carbocation, which, remember, whenever you see a secondary carbocation, you should always be suspicious of that, right? Perhaps there will be a rearrangement, and that is the difference of this problem and the last one. The last one we formed a tertiary carbocation which was stable. Secondary carbocations, depending on the structure, often show rearrangements. And in this case, we can do a hydride shift in order to go from a secondary to a tertiary carbocation, which is more stable. Once it is more stable, we can do a nucleophilic attack using water. We could, sorry, this is actually not what happens. Remember that heat, right, favors E1. So what I actually drew here is what would happen if it was SN1, not E1. So unfortunately, I need to change that arrow, right? So we're just going to change that a little bit. And we're going to be removing one of the carbons at hydrogens at a beta carbon. So here, here, and here are the three different beta carbons. And remember that E1 always favors the most stable product, right? So we're definitely not going to be forming an alkene here because that would be less substituted. If we form one here, this will be tri-substituted. And if we form one here, this will also be tri-substituted. So it probably will end up with a mixture, removing one of the hydrogens here or one of the hydrogens here. So we'll just show one of those, perhaps this one, right? Or we could say this one. So one of those two, leading to a mixture of products. Right, and this one is the more stable E isomer, right? And then also we had removed a hydrogen at the other beta carbon, we would end up with, and I'm going to go ahead and make it the more stable. Oops, put the methyl down here. That's actually the more stable E isomer. Right, so we're going to write E and E just so we know why we formed these and not the Z isomers. Right, these will probably be the major products here. So it's a bit of a confusing one because you can actually get more than one product because they're both tri-substituted. So they're both around the same in terms of stability. Okay, the next one we are going to use sodium ethoxide, and notice that this is a strong nucleophile / strong base, right? So it could go SN2 or E2, but on a secondary alkyl bromide, E2 is the major pathway. So E2 will definitely be major here, right? And it's going to form with a small non-bulky base. It will form the Zaitsev product as the major product. So we have some ethoxide that is going to primarily act as a base to do E2, which is a concerted reaction, meaning all of this happens in one step to give the product. Okay, and this is neither E or Z, so we don't have to worry about that. So we're going to put Zaitsev in here. Okay, this is very similar, strong, bulky base, right? This strong, bulky base is, because it's so bulky, it doesn't usually act as a nucleophile. It usually acts as a base doing an E2 reaction. Because it's bulky, we're likely to get now the Hofmann product. So we're going to selectively remove a hydrogen from the less substituted carbon to make the less substituted alkene. And it happens this way because it's a much faster pathway for it to remove a much less sterically hindered hydrogen. Right, and again, it's E2, so everything is happening all at once. Right, so we're going to get the Hofmann product. All right, the next one, sodium hydride is a strong base, so it will do, very likely do an E2 reaction as well. But it's very small, right, not bulky, so we're thinking again Zaitsev. When we have a ring like this, though, we need to think about which hydrogens are accessible, because we do have the two hydrogens over here, right, and we have one here, but we actually cannot remove this one, because if you draw it out in a chair conformation, it's easier to see why not. Right, so if I draw this structure in a chair conformation, I'm going to put the bromine up an axial. So then the hydrogen here is over here, and this position is blocked by a methyl. And then we also have the hydrogen that's pointed here and the one that's here. Okay. So for an E2 reaction, the leaving group and the hydrogen must be anti-periplanar. Right? So this hydrogen is the only one that's anti-periplanar. Right? This hydrogen is not. That position is blocked by a methyl. So we actually cannot remove those two hydrogens. The only one we can remove is this one, which is the one that's pointed down here, right? The one I circled. So that means that the product will actually have an alkene generated on the left, even though it might seem like I can take this one, particularly with a small unhindered base, I cannot, because of the requirement of the anti-periplanar transition state in an E2 reaction. Okay, for the next question, I think I'm going to take a little break, and it's a very long activity, and I will continue this in another video.